Hello, everyone. Good morning, good afternoon, good evening, and everyone joining in. So, we are at the end of Space Science Challenge by Spaceonova, and it's the second edition, and it has been really successful. We have got quite a number of entries, and many teams qualified for the finals. So, this is the end of Spaceonova, where we have Spaceonova Space Science Challenge, and we will be having the main grand finales on Friday, Saturday, and Sunday over the next 3 days. And to mark this, we have a very special guest today, which is the keynote speech today that will be given by Dr. Tirtha Pratim Das, who is the Director of Space Science Program Office from ISRO headquarters, Bangalore, India. With a PhD in physics at the Cochin University of Science and Technology, he began his career as a rocket technologist at the Vikram Sarabhai Space Center, ISRO, post which he moved to the planetary sciences as a scientist in the Space Physics Laboratory at VSSC, before he took charge as a deputy director in the Directorate of Technology Development and Innovation at ISRO. Subsequently, he contributed to the scientific exploration of Moon and Mars in Chandrayaan 1, Chandrayaan 2, and Mangalyaan missions. Currently, he is responsible for the space science exploration programs of ISRO. Professionally, Dr. Das has experiences in launch vehicle technology with a systems engineering approach, and he has been an experimentalist with specialization in space-borne mass spectroscopy for planetary science missions. A planetary scientist by training as well as science administrator, Dr. Das continues to immensely contribute towards the initiation of several disruptive, futuristic, and innovative space technologies for the space sector. We are honored to have you, sir, today, and the platform is yours. Thank you so much for giving us the time today and agreeing to be on this event for the grand finale of Space Science Challenge. And it's over to you, sir. Thank you. And you can, start.
Thank you very much, Dr. Shreya, for this nice introduction. And today it has been an opportunity indeed to be present in front of this gathering and to be able to present in a very general way how does the field of space sciences excite all of us, and what are the techniques, what are the domains we should study, and what are the techniques which we follow. We are not going to go to the details or intricacies of the science and technology of each topic because that is not possible in a few minutes. This lecture will have a specific objective, that is to give a broad overview, especially to the students who may either take up the space science research as their career in future, or even if they do not take up space science as their career in future, they will at least be aware of these kinds of things that are happening. So this is the humble objective of today's few minutes. So with this backdrop, is it okay to start the presentation?
Yes, definitely, sir. So we will put on your slides.
So is the slide visible?
Yes, yes, your slides are visible.
Okay, thank you very much once again. And as I have mentioned, the title of today's lecture is Space Science Exploration. Science, techniques, and domains will be the areas where I am going to emphasize today. And the first question that comes to our mind is, okay, space science exploration, what, how, and why? So let me tell you at this very beginning, when we say space science exploration, we start with our own solar system because charity begins at home. There are a lot of things to explore, I understand, beyond the solar system, and there is no limit other than our imagination and technology with which we are going to probe the universe. So it starts with the solar system, and then pursuing exploration for extraterrestrial life and activities for sustainability of life beyond Earth. So there are two aspects. One question is very obvious: are we alone in this universe? So if there is any extraterrestrial form of life, that is again another uh, motivation to study the space. And also, if a known form of life like us, the human beings, are put outside the terrestrial environment, how should we sustain beyond Earth? So that is another way to look at it. That is, whenever we are wishing to extend our presence beyond Earth somewhere else. Now, how do we do this? We do this by defining and conducting the space science missions. And while we do this, we engage with academia, and we are in the process of getting engaged with the industries in pursuing this space science program. And last but not the least, engaging in international cooperation for advancing knowledge and capabilities, because space is a common heritage of mankind. So one's knowledge should aid another, and we should grow together as mankind. All these things are aimed to gain scientific knowledge on the past and present states of the solar system. And why to limit ourselves to the solar system? It extends beyond the solar system, the exoplanets, and beyond the entire universe, and predict the future state of Earth and the other planets and Sun. So many of the times in your lecture, you will notice that I will uh, put more emphasis to understand our own solar system. That is, from there we understand that how the things work in the rest of the universe. Okay, so solar system and the components of the solar system will get lot of emphasis in our exploration, and expand human presence to other planets, an alternative abode for the sustenance of human race. Now, when we say space, a very common question that arises is, what is space? So if you ask people what is space, people will come up with different answers. As for example, if you even ask an atomic physicist or nuclear physicist, the person may tell the space with the volume between the nucleus and the electrons, that is also a space, and there is nothing wrong in it. And if you ask an earth scientist what is space, he or she will come up with some answer. If you ask an astrophysicist what is space, he or she will come up with some still other answer. So everybody has its own perspective of space. So when you say what is space, there is always a reference which is drawn with respect to an imaginary line called Karman line, which many of you are aware of, wherein we differentiate between the domains of aeronautics and aerodynamics. So below the Karman line, below the 100 kilometers from the main sea level, um, we are very much bothered about the atmosphere and interactions of atmosphere with the surface of the earth, and the region where the aeroplanes fly, and how the structure of the aeroplanes get interfered with the gas atoms and molecules. So these are all the domains of aerodynamics. And then beyond that, when the atmosphere is becoming sparse, number of atoms and molecules per unit volume is really less. That region is something we tend to call space. But if you ask an earth scientist, to the earth scientist, the space is right from the surface of the earth, which we call the first layer, the boundary layer physics. Okay, and I should also tell here that in 1948, with the foundation of the National Balloon Facility, the Tata Institute of Fundamental Research, Hyderabad, uh, there was the first set of experiments which were conducted to study aspects of the cosmic rays using balloon as a platform. And you can see here in the picture Homi Jahangir Bhabha sir, and in the bottom panel you are seeing Vikram Sarabhai, the founder of the Indian space program, wherein in 1960s we started the exploration of space with sounding rockets. And in the left side picture you are seeing here, whenever I am having to explore the region around 40 below 40 kilometers, I have to take the help of balloons. And if I have to cross the common line and do something beyond, I have to take the help of rockets. And that's how the justification of the sounding rockets came here. And when I have to do something still beyond, I have a few hundreds of kilometers or thousands of kilometers above the main sea level, I have to take the help of the satellites. Now, with this background, let us go one step beyond. So, when we see we are observing space, so one great invention that expanded our horizon was telescope, and it was way back in the 17th, in the beginning of the 17th century, and these telescopes were used to detect the distant celestial objects, which were otherwise not that much uh, sensible with our bare eyes. At once, you attach an imaging sensor like a camera kind of instrument at the end of the telescope, you get an imager. So what you have some optics to see certain objects which are in the distant place, and you are imaging them. Otherwise, you will just end up in looking through the telescope and drawing the same on a canvas, like the astronomers used to do in the olden days. So if you don't do this, if you attach an imaging sensor, you get an imager. That is to study the size, shape, and the features of the celestial body you are interested in. Instead, if you attach a wavelength dispersion component, like a filter or a grating kind of instrument wherein it can disperse the different wavelengths which are coming from the celestial body, you end up in getting a spectroscope. And spectroscopes are used to study different processes happening in a celestial body. Now, if you combine these two features, spectroscope and an imager, you get something like an imaging spectroscope. So with an imaging spectroscope, you study its shape, size, features, as well as the different processes which are happening in the celestial body of interest. Now, what kind of processes we speak about? I have tried providing a list, but this list, as you can understand, is far from exhaustive. You can be interested in the processes of the dynamics of the plasma in sun. You can be interested to study the merger of black holes, supernova explosion, merger of different galaxies, accretion of disks around black holes. You may be interested to see the signatures of the gamma ray bursts, energetics inside the hot stars, or excitation and relaxation of atoms in a planetary atmosphere and surface, and the list gets piled up. Now, when some processes happen, how do you come to know setting from Earth? There are certain messengers which carry this information from those celestial objects to you. So, one such messenger is the electromagnetic waves. Another type of messenger is the cosmic rays, the neutrinos, and the gravitational waves. So, in my very short lecture, I will not consider everything that is beyond the scope of this lecture. As you can understand, the electromagnetic waves coming from the distant objects, uh, they form a very significant part of the observational uh, messenger. And in the domain of the electromagnetic wave astronomy, you can study the timing aspect, whether something is flickering with respect to time, or you can be interested in the spectroscopy aspect to see what wavelengths are coming, or whether there is any absorption of any wavelength. That will tell you a lot of stories. You can be interested in imaging to find a lot of features, or you can also be interested to study the polarimetry of the electromagnetic waves, which tell you a lot of other things. As for example, if you are interested to study whether there is some water ice on any planetary surface, the polarimetry of the signal which you are getting back from the surface tells you a lot of things about that. So now, as I told, each part of the electromagnetic wave spectrum has a story to tell. So I'm not going to read the entire table for you. All that I want to convey to you is, uh, if you see that the wavelength which is coming to you, it is a function of the temperature of the celestial body which is emitting. If you take it in that way, then if the equivalent temperature is very high, greater than 10 to the power 8 Kelvin, you get gamma rays. If it is 10 to the power 6 to 10 to the power 8 region, you get to say X-rays. Similarly, you go on from the hot to the cooler part of the spectrum, you end up getting radio waves, which is about less than a Kelvin kind of temperature that gives rise to the radio waves. And each part of this spectrum has a story to tell you. And not necessarily the temperature has to be this much to have an X-ray, for example. Although it is understood that if you have a body which has really this kind of temperature which emits X-rays, but not necessarily that is the only a way you can get X-rays from a source. X-rays you can get from even from a planetary surface, which is excited to a higher energy level and subsequently undergoes a process of relaxation to emit X-rays. So the physical temperature of the body need not be that. So it is a process which tells you lot of stories inside the celestial, inside and outside of the celestial body you are interested in, and that has given rise to different branches of astronomy like gamma ray astronomy, X-ray astronomy, even multi-wavelength astronomy, hyperspectral imagers, and all these domains are having associated technologies. You make certain instruments which fly to space to do the needful. Now, let me tell you what are the major themes of the space exploration program. So this lecture, I would remind you, is a very common lecture. It is not specific to any particular space agency. It is to give you an overview. Although in the course of my lecture, I will show you some examples from our own space missions. That is a different part of the story. So coming to the different themes, one theme could be the planetary exploration. You're studying the different planets in the solar system, or another theme could be the heliophysics and the space weather studies, the study of the sun and space weather. What is space weather? Many of you are hearing this term for the first time, or many of you might not have much of an idea what does the term space weather mean. We will see in the course of the lecture, including aeronomy. We will see what is that. Aeronomy is basically the study of the physics and chemistry of the outer part of the upper part of the atmosphere of any planetary body. Then astronomy and astrophysics, everybody understands, and exoplanets. Now, these are the major themes. Then how do you study? One way to study is you observe. So when you observe, there are multiple ways to observe. You can design a space mission to observe. You can send it in the form of a satellite or a space probe so that the observation happens from the space. Or you can have ground-based studies wherein you have the proper infrastructure like radars, ionosondes, or telescopes, whatever it is, on the ground, and from the ground you observe. Okay, so every procedure has got some pros and cons. You have to select the best one or the optimal one or the combination of these two for studying a particular scientific celestial body with a particular scientific objective. Another way to look at the problem is, apart from the observations, you can do modeling. So when I say modeling, it is a physics-based understanding of the subject. So you know what are the physical processes happening there, and you know what are the physical processes involved, and you try to build the physics of the whole thing which is going on. That is one way. Another way of modeling, which is an emerging area nowadays, is data-driven approach, which is based on the big data analytics. So we have a lot of data from the observations, either from the space missions or from the ground-based studies or combination of this, and you nurture these observations in a particular format, and you have a mechanism to make sense out of this gamut of data, from where you try to search a pattern, and from this you try to understand what is happening there. And often the physics-based modeling and the artificial intelligence, machine learning-based modeling, they're complementary to each other. So sometimes the artificial intelligence-based modeling may indicate in your physics-based modeling, there is some scope of improvement possible. You add some more parameter and see your model will have a better fit with the observation. So observation, space-based and or ground-based, and physics-based modeling and AI ML-based modeling, you don't see them as independent islands. They are all collective things, and experts from all the things are needed to do a real justification to the space science exploration. One message which comes out of this slide is, in space science exploration, no domain of knowledge is left out. If you are a computer scientist or engineer, or if you're electronics and communication engineer, you're a physicist, you're a mathematician, you will have some role to play here. And another thing which is also of importance is, what are the types of platforms for space exploration? So when I say platforms, it's like this. If you send a balloon to study certain phenomena in space, the balloon is a platform. If you're sending a rocket to study certain phenomena of space, that rocket is a platform. So in the first panel, I have shown here the scientific balloons, and the picture I have shown a balloon which was being flown from the National Balloon Facility TIFR, 40 to 50 up, not 50. It doesn't go. It occasionally it goes up to 50. It is less than 50. Typically, 40 kilometers is the maximum altitude above the main sea level it can study. And then I'm showing you in the second picture a picture of the sounding rocket, which is from our own Tumba Equatorial Rocket Launching Station near Thiruvananthapuram, Vikram Sarabhai Space Center. So that is another kind of platform with which you can probe about 70 kilometers to a few hundreds of kilometers above the surface. Other kinds of platform is satellites. The satellites could be around the Earth, or satellites could be around any other celestial body. In the picture, I have shown an artistic view of Chandrayaan-2 satellite, which is around the moon. Another kind of platform I have shown here is number 4, lander or impactor. So in the picture, I have shown an artistic view of the Chandrayaan-2, the lander which we were supposed to land, but we could not succeed. Chandrayaan-3 anyway is going to have a lander and the rover. So this is a mechanism where you can study the surface of a celestial body, a planetary body to be more specific. Soft landers for prolonged experiments, or you can also have impactors. You don't bother to have a soft landing, you impact, and then while you are impacting, you can study, or you have already impacted and the impact has generated certain disturbance of the surface, some plumes or some craters it has generated. And if you have some other mechanism, as for example, with an infrared camera from orbiter, you are studying what is happening due to the impacts. And impact causes perturbation, the cause and the effects you are studying from some orbiter, either in the infrared spectrum or some other part of the electromagnetic spectrum. So that is another mode of study. And also number 5, I have mentioned about the rovers, wherein you not only land, but you have a mechanism to rove around, typically a few hundreds of meters or around 1 kilometer from the point of landing. These are the rovers wherein you would like to see whether from one point to other, is there any heterogeneity of sampling of the surface of a celestial body, typically that kind of things. Another kind of platform is or mission is flyby mission. Flyby mission is something like this: the spacecraft passes close by a celestial body and conducts scientific observation. It is like this: you are traveling to a destination, but in between, en route, when you are traveling, you are taking some pictures of something which generates interest in you. So in the picture, I have shown an artistic view of the Cassini spacecraft during the Titan flyby. So that is one example. And another one is space observatories. So this is an artistic view of the Soho Heliophysics Observatory. The observatory is launched to space to observe celestial bodies and astronomical sources. So these are the kinds of exploration platforms. So in the previous slide, I have told you about the different domains, observations, and modeling, and how they're connected with each other. And then here I am telling, if you have to observe, what are the platforms you may need to observe and what are the kinds of missions. Then if you go to one step finer details, you would like to ask what are the kinds of instrumentation techniques you would like to use for the exploration of space. So you can also broadly classify these instrumentation techniques into 2 classes. The first is the remote sensing techniques, and the second one is the in situ study techniques. So when it comes to the remote sensing techniques, as the name suggests, you are not intervening, you are not touching the object of your interest from a remote location. You are depending on certain messenger to come from the body of interest to your instrument, and you are making sense of the observation. As for example, reflection or scattering of the solar radiation from the planetary surface and analysis of the reflected signal. So sun is emitting electromagnetic radiation. It is interacting with the surface. Either it is getting reflected or scattered, or it is some part of the radiation is getting absorbed, and it is getting some part of the energy is getting re-emitted with the as the black body radiation, and whatever is coming out, your instrument is capturing and making sense out of it. And here, this whole process itself gives rise to two branches of study. One is spectroscopy, other is imaging, as I mentioned in the beginning of my lecture. In the spectroscopy, analysis of the spectral absorption features, or sometimes it is not absorption. If you're looking towards an active source, you can see certain emission lines also. Okay, and another aspect is imaging. You would like to know the features, the visible features onto it of the celestial body. And another way to do remote sensing is, um, as for example, solar radiation is uh, incident on the surface, and the atoms are getting excited on the surface, and it is undergoing a subsequent relaxation. And when it is undergoing a relaxation, it is emitting photons, and those photons are the ones which are being captured by the instrument in the satellite. As for example, it is a process of X-ray fluorescence, you can say XRF, wherein the X-ray which is coming out of the process of relaxation is being observed by you. And you are going to draw inference about what are the kinds of elements present on the surface. So these are some examples. And another example is, um, say, in the case of active remote sensing. What do you do in active remote sensing? You have the source of energy within your satellite, and you are illuminating the surface of the celestial body of interest. And then from the reflected or scattered or the signal which you get back, you are trying to make sense of the observations. So in the active remote sensing, scattering of the incident radiation from the planetary surface and analysis of the return signal happens. One such example is, say, polarimetric studies. When the studying the polarization of the signal, you can study the surface roughness, surface electrical properties, subsurface hydration, whether water's ice is there. So many things you can study. Another domain I said it is in situ studies. So when it comes to the in situ studies, it is remarkably different from the remote sensing. In the in situ studies, your instrument is swimming within the entities which it is going to study. As for example, if you're having a mass spectrometric observation, it does analysis of the gas atoms and molecules, how much composition are present in a given medium. So it is finding itself embedded in the medium which it is studying at site in situ. Similarly, if you are having a seismometer, suppose you have planted a seismometer on a planetary body, and your interest to study how does the surface, undergo some quakes. So that is an in situ study. Or if you are having a charged particle detector to study the charged particles which are coming from a planetary ionosphere or the surface. So that is an in situ study. Similarly, if you're having a Langmuir probe, or if you're having a Raman spectroscopy for soil sampling, or if you're having an instrument wherein with a laser you break down some sample, and from the plume you study what is happening, what are the things comprising that element, that is also an in situ studies. And sometimes in situ studies are connected with the remote sensing studies. You may think that I am doing in situ studies of certain neutral particles around the planetary body, but once you analyze and once you know the physics, you might be able to use those in situ measurements as a remote sensing measurement to infer what might have happened on the surface and what might have been the processes on the surface or interior of a planetary body that have given rise to these atoms and molecules which you are measuring at a big distance. So in situ studies are often connected with the remote sensing observations. So there should be habit to see the connectivity between these two. Okay, so a great scientist is always in making when the person starts seeing the connections between the apparently disconnected entities, maybe in the domains or the techniques. So coming to the domain of solar system exploration, as we know, the age of the solar system is around 4.5 billion years, and solar system comprises the sun, the planets and the protoplanets, natural satellites, small bodies like comets and asteroids, dwarf planets, interplanetary dust, so on and so forth. Now, towards understanding of our solar system, and it is good to understand because once we get some understanding of our solar system, and if we can extrapolate our wisdom to tell what might have happened or what might be happening in some other solar system in our own galaxy, or if you go to some other galaxy, there may be some other solar system. So if you understand our own solar system, that may be a tool to understand what is happening elsewhere. Okay, so charity begins at home, and then you try to understand the society, the country, and beyond. It goes like this. So again, you go on doing modeling, and with the modeling, you do some predictions, and you send some missions, or you do some ground-based observations, do prediction, do some observations, and you go on refining your models, and that is how the science progresses. And in doing this, you understand the sun, the heliosphere, sun-planet interaction, space weathering, comparative planetology, astrobiology, to name a few of the domains. So now, while doing this, typically, what are the things you may be interested in? Say, when it comes to the sun, you may be interested to study the sun at different wavelengths. You may be interested to study the solar winds. As you are aware, sun emits a lot of particles also, hydrogen, helium, and some heavier particles also come, and they are in ionized form. And they constitute the solar wind. You may be interested to study them, or you may be interested to study the fields, electric and magnetic fields, which are carried with the charged particles. When you are interested to study the planets or the natural satellites in the solar system, you may be interested to study the atmosphere of the celestial body. You may be interested to study the interiors of the surface topography, mineralogy, or whether there is any magnetism, so on and so forth. And this gives rise to the domain of study which is known as comparative planetology. When I say comparative planetology, as the name suggests, how do the planets compare with each other? And when I say how do they compare with each other, not only I mean how do they compare with each other right now when I'm speaking with you, it also indicates how do their paths of evolution compare. See, everything started after the formation of the solar system 4.5 billion years ago. Now today, Earth is like Earth, Venus is not like Earth, Mars is still different, Mercury is still more different. So what is the reason for this difference? Some planets have got different angles of tilt. Some planets are having their intrinsic magnetic field. Some planets do not have. And some planets do have some atmosphere. Some planets do not have. Some planets have got a very high bulk density. Some planets are less in their bulk density. How does it happen? How does the evolutionary path change or make the planets different from one another? There are a few factors which I have listed here. One is the distance from the sun, the mass of the planetary body, its internal energy which causes the internal activity, the chemistry, surface chemistry, or the chemistry of the solar photons with the atmospheric gas and atoms, molecules, outgassing history, presence or absence of liquid water, greenhouse effect, and there may be many other things. And this atmospheric composition and density are also different. It's their mineralogy is different, geochemistry is different. So that is one domain of study. And then, as for example, I will tell you, if we have to study all these things, and especially when you have to study that how the solar system might have been long back, and how the solar system might have evolved, one good celestial body which offers you certain advantages is our own moon, which is very close to us, which is amenable to lot of observational platforms like orbiters, landers, impactors, and you can observe moon from the Earth also. And moon being an airless body, it is devoid of chemical weathering, and the polar regions of the moon are the ones where the solar radiation does not reach directly. It is reaching in a grazing angle, and there are certain craters which are permanently shadowed. And when they're permanently shadowed, just imagine in those areas, solar radiation have not entered since the beginning of the solar system. And those regions have retained the history of the solar system. So understand moon, and you will get to know a lot of things about the solar system. So that is the philosophy. And with this, we have gone ahead with our Chandrayaan 1 mission, then Chandrayaan 2. Here, I'm sorry for the mistake. Here, it should be Chandrayaan 2, which we have launched in 2019, which is still in orbit, and Chandrayaan 3, which is going to be launched in future. And let me tell you, the Chandrayaan 1 and 2, uh, especially the Chandrayaan 1 and the present mission, they have been changing the perspective of the moon. Okay, before the Chandrayaan mission 1 mission was flown, we used to feel moon was as dry as a bone. And this concept was radically changed with the discovery of water molecules on the lunar surface as well as on the lunar exosphere. It was a thought that moon is geologically dead billions of years ago, but Chandrayaan has shown moon is dynamic and volcanically active. It used to be thought that moon's regolith completely absorbs the impinging solar wind photons, but it was proven it was not so. About 20% of the solar wind photons are reflected back to the space as energetic neutral hydrogen atoms. It used to be thought as lunar wake region is the region of space which is having the shadow of the moon. Okay, so it is very simple. It is devoid of any solar influence, but it was proven otherwise. Estimated different populations of ions in the lunar wake, which is due to the influence of the solar photons and some processes of transport there. So there has been lots of um, understanding, increase in the wisdom about the moon because of the Chandrayaan mission. And Chandrayaan 2 mission is having 8 scientific instruments with which it is observing, and it is providing the sharpest ever optical images from the lunar orbital platform, which is about 0.25 to 0.30 centimeter spatial resolution. First ever global mapping of argon 40 has been done in the lunar exosphere from the lunar interior. So lunar argon 40 is very interesting because argon 40 is a gas which is coming from potassium 40 because of the radioactive disintegration of potassium 40. Radiogenic potassium 40 argon 40 is coming, and this is happening deep inside the lunar mantle in a depth of a few tens of kilometers from the surface of the moon. So whenever you see some enhancement in the lunar argon 40, you see that is a signature of some radiogenic uh, features which is happening deep inside the surface of the moon, and which is making itself available through the orifices and fissures which is coming out to the atmosphere. And it also, although it is a lunar mission, there is an instrument called X-ray monitor XSM, which is looking at the sun in our own Chandrayaan 2. It has discovered microflares during the quiet sun period. I will tell what is meaning of the quiet sun, and which also gives some clue to the solar coronal heating problem. And it also happened that unambiguous detection of hydroxyl and water on the lunar surface with the extended infrared observation also happened during our Chandrayaan 2 observation. And fast detection and mapping of trace elements and sodium on the moon with highest resolution elemental maps by the Chandrayaan 2. So shifting our attention to the Mars orbiter mission very quickly. As you're aware, the Mars orbiter mission flew with a set of 5 scientific instruments with the Lyman alpha photometers to study the ultraviolet radiation which is coming from the exosphere of the Mars, methane sensor on the Mars to study the possible signatures of methane, and the Mars exospheric neutral composition analyzer MENCA to study the exosphere of the Mars, its composition, and it how does it get influenced when it is influenced by the solar forcing. It also had a Mars color camera to study the visible images of the Martian surface and the different geological features, as well as the polar ice caps of the Mars. Also, a thermal infrared imaging spectrometer. So, with this suite of instruments, the Mars mission flew. And due to the lack of time, I will just share with you only one or two major results from the Mars orbiter mission. As for example, the Mars orbiter mission has done the first in situ composition measurements of the Martian dusk sector atmosphere. So when it is the dusk in the Mars, what happens to the exosphere of Mars? Because the solar influence dictates a lot what will be the composition of the atmosphere. And in the dusk, we have found the studies of composition of the exosphere depicting the presence of AMU 44, that is carbon dioxide, AMU 28, that is carbon monoxide and nitrogen molecule, AMU 16, that is atomic oxygen. And also, it helped us in understanding how does the exosphere get affected by the solar radiation when sun is directly overhead on Mars or it is the dusk of Mars. It makes some difference. And we also discovered the suprathermal argon, which is having energies, very high energies, which is not otherwise expected that it should happen, which gave some clue about the escape of the atmosphere from the Mars. So we knew that Mars had once upon a time a thicker atmosphere than it features today. So the problem is still not that we have solved everything. I cannot claim that this mission has solved everything. That is not possible. What has happened is the observations feed to the models, and that's how the models get improved, and that is what which has happened. And you're aware of the Aditya L1 mission. In the Aditya in Sanskrit, it means the sun. So you're studying the sun sitting at L1 point. L1 is a Lagrangian point. You know what is the Lagrangian point? A Lagrangian point are the points, there are 5 of them, which are having some specific gravitational uh, veil or gravitational hill features. I will not go to the details only. I will restrict my discussion only to the meaning of Lagrangian 1, which is here. So these Lagrangian points are specific to any two bodies. It is a two-body problem. And Lagrangian point 1 is the point where the gravitational field of the two bodies, they cancel out. Here the gravitational field of sun and the gravitational field of earth, they are getting cancelled out. But you have to remember, this is not a drawing which is in scale. If the distance between the earth and sun is 150 million kilometers, and then the distance between the earth and the first Lagrangian point will be around 1.5 million kilometers. So you have to consider that it is not drawn up with the scale. So with this mission, there will be a spacecraft or an observatory which will be placed around the Lagrangian point 1 in an orbit which is called a halo orbit, and which is going to study the corona of the sun, hard X-rays, soft X-rays. Sun will be studied also in the ultraviolet wavelength, the charged particles which are coming out of the sun in the form of the solar wind, that will be studied, the magnetic fields from the sun, that also will be studied. Okay, so basically this is going to be a solar physics mission, and this will also be an input to understand something called space weather. And before going to what is called space weather, let me tell you about one more thing. Many of you are aware that sun becomes, sometimes very active, sometimes less active in a cycle of 11 years. So there is an 11 years of periodicity, and you will come across this kind of a curve in many places, wherein in the y-axis we are plotting the sunspot number. A sunspot, as you're aware, is a region on the solar surface which is relatively cooler, about 1,000 or 1,200, Kelvin cooler than the rest of the area on the sun, and which are characterized by magnetic fields roughly a few thousands times stronger than the average solar magnetic field. So these are the sunspots, like black patches. They are black because they're cooler, and their numbers vary over time. And when the sunspot numbers are very high, the this is sun has become active, and lot of things come out of the sun in terms of high energy particles, coronal mass ejections happen, solar flares happen, and high fields, intense fields come out of the sun, and this happens over a periodicity of 11 years roughly. And here, this picture is shown, showing that we are somewhere here, 2022, and we are going towards a solar active, solar high right now. The sun is becoming active. So in newspapers also you see a lot of stories about sun is becoming active, some solar storm is happening, some geomagnetic storm is going to come because of some solar event. So these news will become common now as we are heading towards the solar activity. In 2025 around, it is going to have a peak. Now, what is the space weather? What is weather? So let me tell you here, I have crossed 42 minutes in my lecture, but maybe in another 10 minutes, if you give me 10 minutes, I will come to a good conclusion. Sorry for this delay. So when it comes to the space weather, it is something like this. It is an extended weather. So when you say weather, you are well on Earth. You are protected by the Earth's magnetic field. You are protected by the atmosphere around you. But when it comes to the space weather, you are really going to a bigger picture. Okay, you are beyond your magnetic field cone. You are beyond your atmosphere, and you are exposed to what is happening in space. That is, you are exposed to the wrath of the sun. From sun, you are getting radiation, magnetic field, solar wind, solar flare, coronal mass ejection, and that's how the space weather. Okay, many of which we cannot understand sitting on the surface of the Earth. And what happens during the active sun period? These coronal mass ejections and solar flares they increase, and we experience enhancement of the high energy particles within the solar wind, and which are embedded with magnetic fields and flux excess than usual. And these fields disturb the Earth's magnetosphere, and which cause geomagnetic storms. And these are the ones which affect the upper atmosphere of Earth. And that's why when we study the upper atmosphere of Earth, okay, we get to know what is happening as the effect of the solar forcing. So, and this is the branch of aeronomy, as I have mentioned in the beginning of my lecture. So, to summarize, while space weather is the cause, aeronomy, which is the science of the upper atmosphere of the Earth or any other planet to be in general, studies the effects. The ionosphere thermosphere system, which gets perturbed by the space weather events, they affect several utilities like space assets, like satellites or communication and navigation systems. And therefore, the study of aeronomy is not only important from the understanding of the Sun Earth connection or the Earth science in general, but also it is important from the point of view of the vulnerability of the space assets and civilian and defense infrastructure. So, coming to a bit, bigger domain, astronomy, astrophysics. Let me tell you a few words about our own astronomy mission, which is active. The AstroSat, which has flown in 2015. It is a multi-wavelength observatory, which is studying different celestial bodies in ultraviolet, visible, soft, and hard X-ray wavelengths. And it is the first dedicated astronomy satellite from ISRO. And it has involvement of several national institutes like TIFR, Indian Institute of Astrophysics, IUCA, RRI, NCRA for space instrumentation as well as the science. It was launched in 2015, as I have mentioned, and it is presently operating as proposal-based observatory. So people send proposals. I want to observe this, so I want to make use of this observatory for this time to this time. And based on the merit, the times are allotted, and then science comes out of it. The suite of scientific instruments are ultraviolet imaging telescope UVIT, solar X-ray telescope X-ray. So first one is ultraviolet, second one is X-ray. The large area X-ray proportional counters, cadmium zinc telluride imager, scanning sky monitor. So with these suite of observations, it is studying the different celestial bodies, and there have been more than 200 publications so far, about 1400 plus users from 49 countries, about 30 data utilization projects, and the 11th or 12th, not 12th, announcement of opportunity cycle is in progress. And as an extension, the upcoming astronomy mission is XPOSat, which is X-ray polar emitter satellite, which is the first dedicated satellite for polarization measurement in the medium energy X-rays. As I have mentioned, polarization has to tell you a lot of things. not only from the passive observations, but also from the active sources. When the body of interest is an itself an active body, the polarization tells you certain story. So XPOSAT uh, carries two instruments, polix and expect. Polarimeter instrument in X-rays will provide the polarization information in the X-ray range of 8 to 30 keV for bright astronomical sources. An expect instrument will provide spectroscopic and timing information in the energy range of zero point 0.8 to 15 keV. Now, polarimetry, as I told you, is an important diagnostic tool of emission processes that are degenerate with respect to the spectroscopic and timing information. Degenerate means, spectroscopically they are same, some signals are same, timing wise also they are same. If some parameter has to make them difference, is the polarization signature. Okay, so that is another dimension to it. And with the additional dimension of polarimeter as a parameter, you can decipher a lot of processes which are happening. And that is the uniqueness of this mission, polarimetry, spectroscopy, and timing information from the same platform for various bright astronomical sources in X-rays. And how does a space science mission take its shape? You start from a fundamental question and split the question to a set of specific questions, set your target, and then you identify the domains, what you want to study, whether you want to study the surface, interior, or atmosphere, and then you define the experimental platform, as I have discussed in the beginning of the presentation. And then Chandrayaan-2 mission as a case study. Let us not go to the much of the details of it, running short of time. Say, how did the solar system evolve? You go to the moon. Moon is your right target because of certain reasons, which I have already mentioned when I was talking about Chandrayaan. And then you go to the basic sub science questions and identify which are the things you would like to study: elemental composition or mineralogy or imaging. You want to study the atmosphere, exosphere, and then after having this, you go to the instruments. So that's how you start from a fundamental problem, and many times the fundamental problems of nature sound more like philosophy than science. And then they become science and they become technology, engineering, and you arrive at the numbers. And then you define the mission, you define your platform and other things. And when the mission is launched, you reach the desired target, and there is a phase of payload commissioning and verification phase that the scientific instruments are working, whether it is remote sensing or density observations. And then the longest period comes, the science observation phase. And then you receive the raw data from the instruments and generate higher levels of data by incorporating different calibration parameters and other things, different corrections, and then you do analysis and you go for the publications. Having said this, I take this opportunity. I'm at the end of this lecture. Let me tell you about our own Indian repository of the space science data, that is ISSDC, Indian Space Science Data Center. So if you go to visit this website, I have given the URL, you will be able to see how the space science, the planetary science or space science data are archived in different formats in this portal. And to summarize this lecture, we have spoken about what is space, the different notions about the space itself, and I have spoken about the different themes of the space exploration, planetary heliophysics, astronomy, astrophysics. I have spoken about the merits of observation and modeling, different types of observation processes and modeling. I have talked about the different platforms and talked about the different techniques, remote sensing and in situ, and also spoken although very briefly, about how are the space missions conceptualized, and we have shown a case study also how they are conceptualized and what happens after the mission is launched. And we have also discussed about the repository of the Indian space mission data. In between, we have spoken about the domain of comparative planetology, space weather, and also given you the glimpses of a few recent space missions of India with the domains of moon, Mars, sun, and astronomy and astrophysics. With this, I would like to thank you once again for this beautiful opportunity. Hope with my humble effort, I could reach at least some of you, tried giving you the glimpses of what all it is, and hope I could make it successful at least to a certain extent. Thank you so much, and Jai Hind.
Wow. Thank you so much, sir, for the very amazing, insightful lecture. And it
Thank
was
you.
such a holistic information from science exploration to astronomy, astrophysics, aeronomy, and so much of technology and everything. Of course, I'm sure all our audience must have had a very good time to like understanding what goes in the planning of a mission and why we need to explore what, why, and how. So that was amazing. Thank you so much.
Thank
And
you very much.
I think we can open the platform for questions. We do have some questions from our audience. Others, please put in your questions in the comments if you have any. We will take it one by one. So, yeah, we can start with the first question that was kind of covered in your slides as well, I think. Does comparing the planets help us studying the creation of our solar system or otherwise?
Yes, it gives some indication. Uh, as for example, as I have indicated, that different planets have got different features. Like, say, you're having the rocky solar bodies, and which started as the differentiated planetary bodies, let us say. And as you're aware that it started from magma ball, and then let's take the example of the moon itself. It started as a magma ball, which is a ball of fire, and then the heat was lost to the outer space and the crust solidified, and today we see the moon, and in between there have been the processes of bombardment by the small solar system bodies and the ejection of the molten lava from the interior to the outside, and then that's how the muddy regions formed. Even if you take this particular example, it tells you that there have been a process of formation of a solar after the formation of the solar system, formation of these rocky bodies, the differentiated objects. How did they form? Because the process of formation of the differentiated bodies is roughly the same, and moon is an example. Now, after having an understanding of how they might have formed, people will ask what were the chemical processes which were involved here. The chemistry also tells you a lot of about the evolution of a planetary body. Now, if you have to study that, if you have to go to a region where the chemistry is still retained, the chemicals are still retained in the form of volatiles, the region is the moon's permanently shadowed regions. It gives you some clue, okay, about the initial chemicals which were there, which were present when the solar system was formed, which were the initial chemical conditions which dictated the evolution. At the same time, you shift your focus from one planet to the other now. So what happened to the planet Mars? In the planet Mars, the greenhouse gas which has happened, which made it rich in carbon dioxide, and the liquid water has evaporated because of the heat, and because of liquid water evaporated, there has not been a process of significant carbon sequestration. And since that didn't happen, carbon dioxide has increased, greenhouse effect increased, temperature increased. It has been a vicious cycle. So what happened to Venus? So if you see, every planet has got tell a lot of stories about the evolution. So now, if you bring into the factor what are the parameters which make them different, their size. Size plays an important role to tell you how much of the internal energy it is retained, or the distance from the sun itself. Okay, or some planet is having a particular tilt, which is not same from some other planet. So there must have been some process of collision with the solar system body. So all these things, starting from the chemistry and physics, also if you have to go to the study of the isotope ratios, okay, different chemicals with some different abundances of different isotopes, they tell a different story of the creation and the evolution. So not only the study of a particular planetary body, if you are studying different planetary bodies and with a set of different parameters, it really tells you about not only about the origin, also about the evolution. But it is a very simple statement which I am making. When you have to do a real job of starting from a very simple problem, Origin of the solar system and evolution of the solar system sounds very big, but when you split it up into the specific problems, what you should study, and then you should see how many problems are coming, and each problem, how we are going to address it becomes a more elaborate job, and that's how the whole business comes, and that is how the importance of, as I have mentioned, the role of international cooperation comes into picture. So that is the whole story about it.
Thank you, sir, for the answer, and thank you, Vanshika, for the very good question.
Yeah, thank you very much for the question. I appreciate the question.
So next we have a question from Shivam. What is your view on the significance of studying noctilucent clouds, and is ISRO or any other research organizations in India provide the opportunity to conduct research about the same? I think it's more related to aeronomy.
Yeah. So we are in the process, in the process of it. As you're aware, the aeronomy is a domain which is of great interest, and there have been lots of aeronomy missions by many other countries. And one of our aeronomy missions is also under the phase of study. So maybe not right now. Right now, today we may not be in a position to be very specific to answer this. In course of time, when our several missions get matured, we will be in a better position to answer this particular question from our own perspective. And by the way, thank you very much for this question as well.
Thank you, sir. Thank you, Shivam. Uh, Another question is, how can we make Mars a habitable planet? And that's coming from Kartikeyan.
Okay, that is also a very difficult question, because if you are considering the entire planet Mars, it is next to impossible, because if you want to make it habitable, there are certain things which are needed to make something habitable. So if you take an example of a simple human space flight, there's a crew module. You want to make it habitable. So what are the things you need? You need to have, first thing that comes to your mind, a right amount of pressure, air pressure. You have right amount of composition of the air, okay, which the human body is habituated with. Then the temperature, and there are a few other factors, humidity, and there are a few other factors. So when you are telling about so many things, then the first step, if you want to do habitability of Mars, it is better to start with a capsule on Mars. So if you have choose a region wherein you can choose that region to be habitable, then also you have to ask a few more questions. If you are carrying a crew from Earth, placing it on Mars, and telling we have made a part of Mars habitable, that is not correct, right? So if we have to really make a part of Mars habitable, then you have to figure in a few more concepts, like the charged particles or energetic particles which are coming, and the unforgiving environment on Mars. That how you are going to shield an astronaut from. Okay, that is again another question. So, and whether there will be any mechanism to have something like an igloo or a capsule or a habitable zone on Mars, like the way in Chandrayaan 1 we were having a lava tube. That was the discovery from Chandrayaan 1. And now in that lava tube, if we have a mechanism of putting the right amount of pressure and composition, right amount of temperature, you can make it habitable for some time. Whether something you can do the similar lines for the Mars, that thing comes. So right, the correct answer for your question is, don't think about the entire Mars in the beginning. Think about only a part of Mars, then identify the problems and what are the mechanisms to attack all these problems. How will you really create that zone of bubble, and how you are going to protect an astronaut or any form of life inside? And if that is so, and if that has to be sustained, whether you can think of growing some sort of ecosystem or biosphere in that capsule. See, every time if you carry oxygen from Earth or carry some artificial thing, it is still artificial. If you have to think about what you are seeing on Earth, whether you can create the same thing. So whether you can create a biosphere fear bubble there. So that is another question. So you have to go in steps. So for that to happen, You have to understand your own Earth first. So, what is the feedback mechanism of an Earth system? How we are emitting things and how we are getting feedback. Same thing you have to create there, and then you have to go to a bigger scale. How we are protected. With the understanding of all these things, start with a small region of Mars and then proceed. So that is my humble submission to you. And thank you for the question, Karthikeyan.
Thank you. Thank you for the answer. So there's a question. You have worked on several space missions, as you just mentioned. So, what has been the most challenging moment for you during these 8 years?
That is a very intriguing question because challenges come in many forms. One is challenges in designing a mission. Anyway, in my capacity, I have not been in designing a mission. I was more with the science. But when I say in a holistic way, designing a mission is a challenge. To take the example of a Mars mission, so the radio delay itself is very high. It's from 8 to 20 minutes. Okay, back and forth. So how do you command the spacecraft which is around Mars, or how do you command the spacecraft when it is behind Mars? So these are some examples of technological challenges. But before that, the challenge starts like this: you have some notion about the physics of the planets, and the first challenge is how to design your scientific mission, how to select the right choice of instruments for answering certain scientific problems, which will eventually lead to the understanding of something bigger that is there. So very correctly identifying a sub problem and very correctly identifying the set of instruments which would tell you something about the particular scientific thing, that is a very good intellectual problem. That itself is a challenge. And after that, the challenge comes when your instrument is started, it has started giving data, and what are the kinds of interpayload science you can do. Okay, suppose one mission has carried some 10 instruments. Each instrument is studying some aspect or the other. Now, how you connect the observations of different instruments in a given mission to get a good perspective of that celestial body understanding, that is another challenge. And going beyond this, similar missions which have been flown or any ground-based observations which might have been there, how to collect, which will have something to say with that scientific question. How do you integrate all this information to give the answer? Then the challenge comes, which many of us have to look into. What are the questions that are raised out of this? See, when you have sent a mission, you thought you have given answers to certain questions. Eventually, if you have not raised a few questions, there is something wrong there. So you must have raised a few questions, and how these questions feed into a new mission. Okay, this thought process is another challenge. So everything is a challenge. Some challenge is in the technological domain, and some challenge is in the intellectual domain. Okay, and when you see the thing holistically as a scientist, every challenge should keep you energized. Okay, and when you are splitting yourself as a technologist or a scientist or a data analyst, you get the challenges in the form of smaller problems. Okay, so if I have to pinpoint the most challenging moment, I cannot answer. That's why I have tried giving you a view what are the challenges could be in different, in different perspective, from the very high perspective to a very sharp role which you might be playing in the role of a mission. So that is my submission. And thank you. This is a very good question. I appreciate whoever has asked this question.
Thank you, sir. So, just a follow-up question to that: how important do you think the a clear communication between the teams that are involved in a mission, like the engineering teams and the science teams? How clear, how the communication between these teams affect space mission, for example?
It affects. Suppose you make an instrument. You have made one, say, imaging spectrometer, and there is an optics and there is a filter. So the engineers have placed a filter in such a way that it is blocking some of your light in some pixel. And suppose that pixel would have told you something very, very important. So that should not happen, right? Now the answer is this is very important, no doubt about it. But I will tell you, if this communication has not happened, it may lead to something which is irreversible. You will fly your instrument, but that instrument might not work in the optimal fashion. So what you should do is, in the beginning itself, it always starts with a very few people. Any idea? Na? One person sees the dream, and then at the end of the mission, there are so many people. But in between, when the thing grows, one person, the dream goes to the two, three people. Small team is from study team, then goes to a task team. So every time there should be a flow of blood. This blood is information, and this information should go in terms of documentation. Speech is fine, documentation. And if there is a change which is proposed, the change should be known to everybody. So the document should have different versions, and there should be a version control. And why there is a change, it also should be noted. So it is a philosophical realm that you start from a fundamental question, but that philosophy, when it is materialized, it has to go through a process, and this process should be through a discipline which you have correctly asked. If there is a lack of communication, what happens? Catastrophes can happen. Thank you.
Definitely. Thank you so much. So, we have another general question. So, what are your advice to the young generation who wants to get into the space field? Recently, actually, there was data that most of the Indian young people, youth, like 24% of our youth, wants to work in the space field. So, what are your opinions or advices to them?
A few things are there. Number one is, space is multidisciplinary. Space field is multidisciplinary. So anything you study, you rest assured some connection is there with us with the space exploration. So first advice or suggestion is, study your own domain well. If you are a computer scientist, you study that well. You by heart your subject. That is very much. You study physics, chemistry, whatever. Space comes next. Okay, that is the first advice. Second thing is, whenever space excites you, you try asking yourself, what about space excites you? What about space is somebody may be interested in the aspect of habitability of outer space, or somebody may be interested in the origin of universe. What happens in the first 3 minutes? That kind of question. Now, the kind of evolution the first person will happen, and the kind of evolution the second person will happen may not be the same. So you ask yourself, what is your domain that excites you, and accordingly identify what are the kinds of popular science books or semi-popular books you have to go through. Because from the beginning itself, if you study some uh, very specialized books which you may not be able to appreciate right in the beginning, your interest will die. You try to identify the authors who write in a very easy language, like Stephen Hawking's book, or in Nallikar's book, to be a few examples. And then, after having understood those, you will see your excitement will increase. Then you see the kinds of missions which are happening in your line of interest. There are several space agencies. What are the space agencies doing? Why they are doing? So you're gradually going to the specifics. As you are going to the specifics, you see what you are studying in your curriculum. So there will be a time when you might have studied your domain. Then there will be a time when you're going to take the special papers. And when you're going to go to the taking the special papers, you choose accordingly, which will help. And in higher studies, you choose your alma mater accordingly, the institutions accordingly, with the institutions which will give you the domain. And at the same time, one advice is, suppose you don't get into the alma mater or some institution which you wanted to get in, don't get disheartened, because nobody has said that if you have to study a solar corona, you have to study in a particular institution. Nobody has said that. Okay, before that institution was there, solar corona was there. somebody has contributed a lot there. So don't go by that. And at the same time, once you grow, try to attend different conferences. These conferences will tell you different advances which have happened, and often in the conferences there will be opportunities to interact with the speakers. Often reading textbooks may not lead to the proper goal. Talk to the people, see who all are doing, build your connections. Okay. After having built your connections, you will know which lab you should go, and then things will follow. I need not extrapolate much on this. Yeah.
Definitely, it's great advice. Thank you so much. I think that's very helpful for all our viewers, and also will spread out the message to all our participants that we have. So we are almost nearing the end of our session today. We just have a couple of general questions that we'll quickly complete. So, sir, I know you are a great writer. I have listened to many of your stories on YouTube, and also you're a great musician. Like you play tabla, and I've been following you. So, how important do you think it is to pursue other interests for our overall development, and also to pursue our academic interests? How does these interests come in together?
That is a very, very important question, and thank you for this. It is like this. It is understood that I also feel a training of music gives you a better handle to understand the abstract. I will give you one example. Example is like this: if you have to teach quantum mechanics to a person, how an entity sometimes behaves like a particle and sometimes behaves like a wave. Okay, that gives you a challenge itself how to explain. But when you go to music, when you play the musical notes, that musical notes give you the shorts give you different feelings. That sare gama padhani, kamal and tibra, 12 of them, they give you different notions, different aspects. Okay. Now all these things are waves, but the kinds of uh, sensation that you get to have in your senses, as if something has touched you, that is a particle. Okay, something has you have been touched by something, that is a particle. Okay, you take one more example. You tell about the, say, in the atmospheric sciences, take one example. You are having a cloud condensation nucleus that has formed, okay, invisibly at some part of the sky, and around it moisture has started forming. From the ground, you are seeing a sky which is full of cloud. There is a cloud condensation nucleus. In music, you have one swara, okay? With the sa, you have given different knees, ni, and then around the sa, there has been formation of knees, like Mega Mallar, you have created the accumulation of clouds, okay? So whatever you're telling or stamping as science, that is a particular way to look at it. Whatever we have stamped as music, it is a particular way of looking at it, but which is still at a more fundamental way, fundamental realm of human mind. Similarly, for literature, the kind of words you are going to put to express a sentence, the weight of the words, that has got some connection with the weights of the music when you are creating a music. And that same thing is going to happen, the same analogy goes when some fundamental particles build, whether it will become a hydrogen or helium or something else, it has got some analogy there. So in order to understand something abstract, if you have a musical training, or if you have a sense of appreciating something which we call humanities, that gives you a better handle to makes you more prepared to appreciate the more abstract concepts of the science itself. So that is important. So that's how I see.
Wow, that's an amazing answer. Looking into humanities through scientific perspective. Wow. Yeah. And to end with, we have just one last question. Which book or movie inspires you the most or has been instrumental in your journey so far?
A difficult question. Similar question would be if I convert the question in this way, if I have to go to a space mission and I am allowed to take only one book, which book I will take? If you ask me this question, I will have a list of the books. But when I am given no option but to carry only one book in a space mission, which book I will take? That book is Ramakrishna Kathamrita.
Ramakrishna Katham. Thank you, sir. Great to know about that. And with that, we will end our session today. Thank you so much, sir, for your time and for the very insightful presentation and the answers. I'm sure everyone enjoyed here on whoever joined us live. And yeah, I would just like to end with giving some information about the Space Science Challenge that we are nearing end to. So Space Science Challenge 2022, it is initiated by Spaceonova with the objective to induce problem-solving skills, design thinking, and solution-oriented mindset among the students in the field of science, space science and technology. And this challenge has been categorized into three categories, namely the space robotics, satellites, and rocketry. And it was conducted in 4 rounds over 3 months. So the prelims started in May, and now we have the finalists that will be presenting to a panel of judges who are experts in these categories, and will be going through the finals today, tomorrow, and on Sunday. So we will have the next version of Space Science Challenge next year. So those who missed out this year, keep an eye and definitely apply, and it's free. So definitely give out your ideas and participate. It's gonna help you in your own development to develop your problem solving skills or understanding the space science and technology field even better. With that, I would like to end. Thank you so much and see you, everyone. Bye bye.